Good afternoon. Welcome to EduSat Network. Friend, today we have another lecture on chemistry, and the precise topic is spectroscopy. In the last lecture, we discussed about the fundamentals and historical perspective of spectroscopy. Today we will move further and we'll talk about the atomic spectra. And for discussion on this very topic, we have in the studio Dr. Rita Kakkar. She teaches chemistry in Delhi University and her area of specialization is spectroscopy. So certainly her knowledge and experience will help us to understand this topic and will guide us how to study the atomic spectra in a spectroscopy. So on her behalf, I welcome her and request her to start the lecture. Welcome.
Thank you. So good afternoon once again, and today we'll start from where we left off yesterday. That is, we discussed historically where spectroscopy started and what information, how some great people of that time, physicists and chemists, they helped us understand quantum mechanics and spectroscopy, and the knowledge that we learned from all that, how we put it in practice today. The first topic that we are going to take up is atomic spectra, because atomic spectra is historically the most important, because this is what made us learn about quantum mechanics and spectroscopy. And not only that, it gives us insights about angular momentum and many other concepts that we are going to use later on. And before I start, I'll just briefly recap what we learned yesterday. Yesterday we talked about the structure of matter and electromagnetic radiation. Now what we learned is that both electromagnetic radiation and matter, they display dual behavior. By that we mean that they can behave like waves and they can behave like matter, they can behave like particles, whatever is the need. And electromagnetic radiation consists of waves where we have perpendicular electric and magnetic fields. When it interacts with matter, the electric field of the radiation, it interacts with the dipole moment or electrons of the molecule, and if the frequency of the radiation matches the energy difference between two energy levels, transition takes place. Today we'll talk about a special kind of transition that takes place in atoms, and this is atomic spectroscopy. In atomic spectroscopy, we only learn about the only about the electronic structure of molecules and nothing else, because atomic spectra deals only with electronic energy levels. There cannot be any rotational energy levels, there cannot be any vibrational energy levels in an atom. So we'll only learn about the electronic energy levels. Yesterday's lecture told us that the modern atomic theory, it arose out of studies of the interaction of radiation with matter. In fact, the first ever spectra that was recorded was by Balmer, and he was able to explain the lines in the hydrogen spectrum using his spectroscopy. And that is why this is the area of spectroscopy that was understood first, and we have a lot of knowledge of it thanks to lots of people, physicists and chemists who worked on this. Now, another reason that I am taking up atomic spectra is there is no interference with rotation and vibration, and generally the peaks are very sharp, and it is generally called line spectra because the peaks are sharp, because only electronic transitions can take place, and in molecules both rotational and vibrational transitions can also take place, and so there is a lot of complication that we can avoid. Now when you look at molecular spectra, that even if you compare for hydrogen atom and hydrogen molecule, both are the simplest element ever, and what we find is that there is a lot of difference between the molecular spectra and the atomic spectra. While the atomic spectrum has relatively few lines, the molecular spectra has a large number of lines because of interference with other phenomena. So that is the reason that we are taking up atomic spectra first. Now let us have a look at the hydrogen atom spectrum, which was the first one to be seen. And when atoms are heated, or you pass a discharge, electric discharge through hot atoms, they emit radiation. Now it appears as a series of discrete lines characteristic of the particular element, unlike the continuous curve that was observed for the black body. Now what is the kind of information we can get from these lines? Again, I go back to history, and it was the Balmer series, perhaps because this was in the visible region, that was the first that was observed, and he observed that different wavelengths, I have listed the wavelengths here, 656.2, it was in the red. There were discrete lines, these lines and nothing else. 486.1, there was a blue line. 434 nanometers, there was a blue violet radiation emitted, and 410.1, there was violet radiation that was emitted, and he was able to fit his radiation into the Rydberg formula. This is the type of graph that he obtained, and he fit it to an equation where nu bar, yesterday we said that this is a wave number. It is generally expressed in meter inverse or centimeter inverse. Centimeter inverse is a unit that is still being used because it is convenient. RH is the Rydberg factor that Rydberg obtained, and 1 by 2 square, because we know that the Balmer series was emission from any higher level 3, 4, 5 to the second level. So the wave number could be exactly expressed in this, where RH was a universal constant, and this is called the Rydberg constant. Now we cannot explain all these lines unless we believe that the quantum mechanically the energy levels are discrete, they are not continuous, and the energy levels are quantized. Now, Balmer discovered that the lines in the visible line spectrum of hydrogen fit into a simple equation. It was Rydberg who found that it is not only 1 by 2 square, it could be any number, and you can, by using different values of N1, for example, 1 will be for the Lyman series, which was not observed so soon because it was in the UV region, and then the later lines, Brackett, Phone, and Paschen, all of them were also in the IR region, which was not known at that time. And using all this, Bohr was able to find a model where he was, here the Rydberg constant is expressed in another unit, joules, and here its value is 2.18 into 10 raised power of minus 18, that the energy of the nth level of the hydrogen atom is quantized, and it is given by this formula. And using this formula, Bohr was able to arrive at a formula for predicting the energies of different levels of the hydrogen atom, and this is where we have shown the energy levels. The first one is equal to minus RH by n square, so it is equal to minus RH. Next one, n is equal to 2, it becomes minus RH by 4, then minus RH by 9, and so on. It is divided by n square, and n can only take on discrete values, n can only be an integer. He called it the principal quantum number. Bohr was able to obtain only this quantum number, and this is later called principal quantum number, and it is given a symbol n. The energy of the hydrogen atom, it was found, depends only on this quantum number. And you'll recall that yesterday we said that Bohr's quantum theory required that the orbits have quantized angular momentum values, and he was able to get the energy levels. Now, the colors from excited gases, you will find that they are characteristic of the element. Sodium has a different pattern and hydrogen has a different pattern. The reason that the patterns are different is because they have different kinds of energy levels, because the atomic number is different. Both sodium and hydrogen atom, they have one electron in an s level, but yet their spectrum is different. Now, this is how we can summarize. There are, you can look at the spectra of atoms either as an emission spectrum or as an absorption spectrum. If you take a hot gas and you look at its spectrum, you will get discrete line from the emission, because a hot gas is in an excited state, so the n value could be very high, and the electron drops from a high n value to a lower value. Or alternately, you can shine electromagnetic radiation of the correct frequency on a cold gas and make it get excited to a higher energy level. Now absorption is taking place, so this is called an absorption line spectrum. The important thing to observe is that the wavelengths of the emission line spectra and the absorption line spectra, they exactly match each other. What this implies is that the higher energy, from the higher energy level to the lower energy level, or from a lower energy level to a higher energy level, the same amount of energy is required, and this means that the energy levels are fixed. And because for every element you have a different kind of spectrum, using this kind of spectrum you can find out what element we are talking about, and this has been used to find out what are the elements that are present in near the sun and so on in the solar system, by looking at the emission spectrum from solar radiation. And you'll see that mercury, neon, helium, everything is characteristic. It depends on the element, and you will be able to characterize the spectrum. Now these are for sodium. Again, you will find that the same lines are observed in the absorption spectrum and in the emission spectrum. Depending upon what technique you want to use, you will get identical kind of spectra. Now, Bohr had postulated, this was just a postulate, that that radiation is quantized. That means that every photon has an energy corresponding to its frequency, which is equal to h nu. And he said the transitions can only take place from one level to the other if the energy exactly matches and it is equal to h nu, which is the energy difference between the two energy levels. And he was able to show that, I have already shown this equation, that it is equal to the Rydberg constant expressed in joules divided by 1 by nf square, because energy is generally expressed in joules, and when Ni is greater than Nf, then energy is emitted because the initial state is at a higher energy level than the final energy level. If it is the reverse, then energy is absorbed to go to the final energy level. Now, Bohr's model had certain limitations. At that time, it was an absolutely new concept, and it was able to explain many of the phenomena related to spectroscopy. We were able to find out explain the hydrogen and hydrogen-like spectra, but there were certain limitations to his model. It was only able to explain for hydrogen-like and hydrogen atom, and as we know that electrons cannot be described completely as small particles, they also have wave character. This he did not take into account. He was talking about orbits. We now know that the energy levels are quantized, of course, like he said, but the electrons have a wave character. That means you cannot talk about precise orbits. The second thing is, at that time the spectrophotometers were not so good. Later on, higher resolution spectrophotometers, we were able to see that each line that he saw was actually a doublet. That means there were two lines which were very close together. The spectrophotometers of that time did not have such high resolution, and that is why they were not able to see the two lines. But later on, the better spectrophotometers were able to show them as two lines. Now, the improvement over Bohr's model was that Schrödinger, he realized that both wave behavior and particle behavior is displayed by electrons. So, you cannot describe electrons as either particles or as waves, and he devised a new equation based on both the properties of using the de Broglie principle also, and he wrote a wave equation, and this is the accepted form of the wave function. We still use that the Schrödinger equation to find out the wave function of particles, and using that the hydrogen atom was able to be completely solved, and we had a picture that was able to explain every aspect of the hydrogen atom spectrum, which Bohr's model was not able to explain. So, when you solve the Schrödinger equation, you get something which is called a wave function. It was Born who suggested that this wave function is actually not important. What is important is the square of the wave function, which gives the probability density of finding a particle in a certain region of space. So, now we have something contrary to Bohr's hypothesis, which said that there were certain orbits and electrons were particles which were revolving just like the stars are revolving and so on, planets are revolving in the solar system. Now, the square of the wave function, it gives you the shape of the electronic orbital. If you plot contours of electron density, you are able to get the electronic orbital. The square of the wave function gives the probability of finding the electron, that is, it gives the electron density of the atom. Now, if we solve the Schrödinger equation, we get wave functions and energies for the wave functions. We get discrete values of energies that Bohr had postulated, and we also get the shapes of orbitals. Instead of orbits, now we talk about orbitals. Now, Schrödinger's equation, it gave us 3 quantum numbers. Recall that Bohr was able to get only 1 quantum number, but Schrödinger's equation gave us 3 quantum numbers. The first quantum number that he spoke about was the principal quantum number n. This is the same as Bohr's n, and we find that the energy of the hydrogen atom depends solely on this quantum number. As n becomes larger, the distance from the nucleus of the orbital keeps on increasing, and the energy of the orbital keeps on increasing. It becomes less negative. solution of Schrodinger's equation also gave us another quantum number, azimuthal quantum number, which is related to the angular momentum. This quantum number depends upon the value of n. We all know that the maximum value of this is equal to n minus 1, and it can have values starting from 0 up to n minus 1. We also assign letters depending upon the value of L. That means 0 means an s orbital, 1 means a p orbital, d orbital it is equal to 2, and so on. For f it is equal to 3. Usually we do not go beyond these, but after that it is all alphabetic, g, h, I, j, and so on. Then this angular momentum is also quantized, and not only is it the total angular momentum given by L, and which is quantized, it is also its z component, which is quantized, and this is given by another quantum number ml. This quantum number depends on the value of L. It can have 2L plus 1 values starting from minus L to plus L through 0. So that means it depends upon the 3D orientation of each orbital. So depending upon the 3D orientation, we have different values of the quantum number. Now, I'll briefly give the relationship which you all know, that there is a relationship between the values of n, L, and ml through n is equal to 4. When n is equal to 1, the only value of L which is allowed is 0, because I told you that n minus 1 is the maximum value of L. This becomes, now we first write down the n quantum number, which is 1, and then like I said, L is equal to 0 corresponds to S. This is 1S, and the only possible values of ml are 0, because L is equal to 0, and the only possible values are from plus 0 to minus 0, which means 0. So there is only one orbital in this subshell, and the total number of orbitals in this subshell is equal to 1. When n becomes equal to 2, now L can have two different values. L can have a value of 0, and L can also have a value of 1. When L is equal to 0, we call it a 2s orbital, because like again L is equal to 0 corresponds to S, and we first write down the principal quantum number, and ml can now have values again from plus 0 to minus 0, that means a single value, and there is only one value. So there is only one 2s orbital. The next orbital is when L is equal to 1, we call it 2p, because when L is equal to 1 it is called 2p, and ml values now can be 1, 0, and minus 1. Recall I said 2L plus 1 values, so this means 3, and there are 3 such orbitals. The total number of orbitals when n is equal to 2 becomes equal to 4, and so on. We can keep on going up to n is equal to 3, n is equal to 4, and so on, and the values increase as n square, 1 square, then 2 square, 3 square, and 4 squares, 5 square, and so on. And this is how I have pictorially shown, but this is only for a single electron system, which could be a hydrogen atom, it could be a helium plus ion, lithium 2 plus ion. Any system which contains only one electron will be described by this. The many electron atoms, there is a difference. Here we were talking about orbitals which had the same energy. As I told you, the quantum number, the energy depends only on the n quantum number. So all the 4 orbitals corresponding to n is equal to 2 have the same energy. This is called degeneracy. Orbitals which have the same energy are said to be degenerate. In hydrogen atom, we have a set of 4 degenerate orbitals for n is equal to 2, and for n is equal to 3 you have one 3s orbital, one 3p orbital, one 3d orbital, all having the same energy. This is very important to remember. In hydrogen atom, 2s, 2p orbitals have the same energy, they do not have different energy. Now when n becomes equal to or greater to than 2, the s and p orbitals now do not have the same energy. In fact, the 2s orbital will have a lower energy than 2p, and this is because of the shielding effect. The 2s electrons, we do not have time to discuss the radial distribution of the orbitals, but if you look at the radial distribution of the orbitals, the s and p orbitals, they have different radial distributions. The s orbitals are able to penetrate more. By that we mean that they are closer to the nucleus as compared to the p orbitals. Now when the p orbital is not able to feel the entire effect of the nucleus, and that is why it has a higher energy as compared to the s orbital. And the offered diagram for a multi-electron orbital will be something like this. You have 1s orbital, then 2s slightly lower in energy as compared to 2p, similarly 3s, 3p, 3d, it is always in this order. 4s, 4p, 4d, 4f. This is the order in which the energy levels are distributed. Now, we have also talked about the Pauli exclusion principle yesterday, that what we find is that the line spectra of many electron atoms, it does not consist of just a single line, it consists of multiple lines. Stern and Gerlach, they designed an experiment to explain why this is found. What they were able to find is that there is another quantum number which is needed to describe the system completely, even the hydrogen atom completely, and this is the spin quantum number. It does not have any classical analog, but I'll try to explain it classically. It is as if the electron can either rotate in a clockwise fashion or in an anti-clockwise fashion, and both of these have the same energy, but these are two orientations which are physically possible. We assign a new quantum number besides the N, L, ML and S quantum number is a new quantum number that we define, and again, just like for L you had values corresponding to plus L up to minus L, you have two values here, plus half and minus half. Both of these correspond to different orientations of the spin quantum number. Yesterday we also talked about the Zeeman effect. Now in the Zeeman effect, when you apply a magnetic field, you find that the lines are split up corresponding to different ML values. The same thing happens here. If you want to see both the MS values, you will have to apply a magnetic field, otherwise they are degenerate. Both spins have the same energy. Now we come to Pauli's exclusion principle, which is actually a very complicated principle, but simply put, the way it is taught in school, it is that no two electrons can have the same set of 4 quantum numbers. Actually, what it states is that the total wave function of a fermion, an electron is a fermion, should be antisymmetric with respect to electron exchange. But the outcome of that principle is that no two electrons can have the same quantum number. That means in each orbital you will be able to put in just 2 electrons, one with spin up and one with spin down, if the rest of all the quantum numbers are the same. Now when you apply the Zeeman effect, you find that one of the spins goes up in energy and the other one goes down in energy, and this is the principle behind electron spin resonance, which we will not talk about because we are talking about other forms of spectroscopy. But this degeneracy is lifted in the presence of a magnetic field, because what this signifies, the MS value signifies, is the orientation of the spin with respect to the external magnetic field that you have applied, and this is called the Zeeman effect. Now we also have Hund's rules that we talked about. There are 3 rules. You start filling up the orbitals starting with the lowest n value because they have the lowest energy, and then you keep on moving upwards. No two electrons, remember this, no two electrons can fill one orbital with the same spin. So if you have put one with, we call these two spins as alpha or spin up and beta or spin down. When you put in both these electrons, one will have an alpha spin, the other will have to have a beta spin, otherwise Pauli's exclusion principle does not allow us to put these in the same orbital. For degenerate orbitals, electrons fill each orbital singly before any orbital gets a second electron. And now this is Hund's rule, which is called the Hund's rule of maximum multiplicity, that if you have orbitals of the same energy, don't try putting both electrons, one with alpha spin and beta spin, in the same orbital. If you want to get the ground state, you start filling up all the degenerate orbitals one at a time with the alpha spin, and once you have exhausted all the orbitals which have the same energy, then you start putting the next electron with beta spin in one of the same orbitals. So for example, when we talk about electron configurations, this is how we know, this is how we write down the electron configurations. We'll start with sodium. Sodium has 11 electrons, and the 1s electron we first put in alpha electron, and this is the lowest energy, we put another beta electron, we can put in 2 electrons. The next energy level is 2s, again we put in 2 electrons. We are left with, we have already put 4 electrons, we are left with 7 electrons. Again the 6th electron is completely filled, and the the lone electron goes to the 3s orbital. And this is the reason, like hydrogen, they have, all alkali metals have 1 electron in their outermost shell. This doublet that I talked about was not so much visible in hydrogen atom, but when you go to sodium, potassium and so on, when the number of electrons increases, the difference in energy between the two between the doublet peaks keeps on increasing, and that is why the sodium D lines were some of the first lines that were observed. Potassium, as you know, shows a lilac spectrum, lithium shows a red spectrum, but they show a spectrum which is very similar to hydrogen atom because they have a single electron in a 3s orbital. Carbon, again we start putting in 2 electrons here, 2 electrons in the 2s orbital, we are left with 2p electrons. Now it is very cumbersome to write down the electron configuration of all the elements. Here I am talking only about elements which have atomic numbers like 11 or 6 and so on. But you cannot, when you talk about transition metals, there are so many electrons that have to be filled in. It becomes very cumbersome to write down the electron configuration. So scientists have devised a new method of putting all this information very succinctly, and this is with respect to a term symbol which is of this form. 2s plus 1 gives you the spin multiplicity. If s is the spin quantum number, then the total number of states which have the same energy is given by 2s plus 1. Remember that the energy does not depend upon the spin quantum number, so all orientations of the spin have the same energy in the absence of a magnetic field. L is the total angular momentum, and L is the total orbital angular momentum, and J is the total angular momentum. You will also observe that instead of small s that we use for writing the spin, or the small l that we used for writing down the azimuthal quantum number, the term symbol has a capital L and a capital J, and J is the total angular momentum. What do I mean by the total angular momentum? You know that the angular momentum is equal to I omega, where omega is the angular velocity and I is the moment of inertia. There is a spin angular momentum and there is an angular momentum due to the orbitals, and this is given by L, and the spin angular momentum is given by S. Now both are vector quantities. Both of them can couple with each other. They may either be in the same direction in which they will add to each other. This is vector addition that I have shown on the right. J is equal to L plus S, that means you draw an L vector and you draw an S vector and see where the arrow ends, just like vector addition, and you get a new vector which is equal to J, and this is equal to L plus S. And this is what we mean by the total angular momentum. The L quantum number, just like the orbital angular momentum that we were talking about, can take on values like 0, 1, 2, and similar to what we did for the electron configurations, we again have symbols like capital S for 0, capital P for 1 and capital D for 2. Again, we are not using small symbols, we are using capital symbols. For that, for hydrogen and sodium, I told you that they both have a single electron in the s orbital. So the how we write is 2s half, in the sense that there is a single electron. When you look at sodium, you ignore all the filled orbitals because they will not contribute to the angular momentum. That means we do not look at the 1s2, 2s2 and 2p6 because they are completely filled orbitals. So they will not contribute to the term symbol. We only look at the 3s1. For hydrogen, we will be looking at 1s1. For lithium, for example, we will be looking at 2s1, 4s1 for potassium and so on. Now there is a single electron, and this is in a s orbital, so its total spin is equal to 0. Its total orbital angular momentum is equal to 0 because for s the angular momentum is equal to 0. There is a single unpaired electron which will have an s value of half, so 2s plus 1 will become equal to 2. It is an s orbital, and J can take on values. J is the total angular momentum which can take on values starting from L plus S if they are in the same direction to L minus S and the values in between by subtracting 1 each other. In this case, because L is equal to 0 and S is equal to half, there is only one possible values, and that is equal to half plus 0 or half minus 0, both of them are equal to half. So the only state which is possible is equal to 2s half. This tells us a lot about the orbital, the type of electron configuration without writing down the whole thing, and it also tells us that hydrogen and sodium have the same kind of electron configuration. Similarly for helium, You may have the helium excited, the ground state will have 1s0 because you have two electrons which are paired. That means one will have ms is equal to half, the other one will have ms is equal to minus half. The total ms value will be equal to 0, which corresponds to s is equal to 0. 2s plus 1 is equal to 1, and the only possible value is equal to 0 because L is also equal to 0 and S is equal to 0 also. So, J can only take on a value equal to 0. In the excited state, when you put one electron in 1s orbital and the other electron in for example a 2s orbital, you also have the possibility of what is called a triplet state, because now since they are in different orbitals, the n quantum number is different. One electron will be in the 1s orbital, the other electron in the 2s orbital. Now both of them can have the same spin, and so if both of them have the same spin, say plus half, the total spin can be half plus half, which is equal to 1. So 2s plus 1 will become equal to 3, and since s is equal to 1 and L is equal to 0, you have one value of J which is equal to 1. Similarly, for carbon, we find that the number of states keeps on increasing because now there are two unpaired electrons. Again, we will not look at the 1s electrons, we will not look at the 2s level also because that is also completely filled. We will only look at the 2p electrons, and we have three states which come from this, and this is the triplet p state, the singlet d state, and the singlet s state. A state with the spin multiplicity of 3 is called a triplet state. One with spin multiplicity of 1 is called a singlet state, and doublet, for example, if the spin multiplicity is equal to 2. Now in light atoms, that is generally when Z is less than 30, something like up to bromine, for example, in that case the electron spins S interact among themselves, so they combine to form a total spin angular momentum S. The coupling is between the spins and the orbital angular momentums themselves first. So how you get the S capital quantum number is that you add up all the spins of all the electrons which are there, and you get the total angular moment, spin angular momentum quantum number, which is called S, and this is given by the summation of SI values. What is happening is that all the electrons, they are coupling together, and all the electrons are coupling together and adding up their spins, and this is how we get. Same thing happens in the case of orbital angular momentum. We get a new kind of quantum number which is L, and L is given by summation Li. Now these individual capital L and S, now they interact with each other and combine to give a J quantum number. This scheme of coupling is called Russell-Saunders coupling or LS coupling, where you first all the angular momenta of all the unpaired electrons will combine, then all the spin angular momentum of all the unpaired electrons will combine. We get a quantum number S capital and we get another quantum number L capital, and we find that the total angular momentum J is now given by L plus S. So this is the kind of coupling that happens. Suppose you have L1 and L2, you get the L total by doing a vector addition, which is quite complicated, but fortunately we are able to. There is a Clebsch-Gordon series which tells us that you take the electrons, you keep on adding both the orbital angular momenta quantum number L1 plus L2, keep on subtracting 1, take the absolute magnitude until you get L1 minus L2. Same with S, and once you've got the capital L and you get the capital S and the capital L, you can combine J is equal to L plus S, again vector addition that I have shown at the bottom of the figure, and again same thing we do, L plus S, plus S minus 1 up till L minus S. It seems complicated, but I'll take up a few examples and you'll be able to understand it. The other kind of scheme, I told you that the Russell-Saunders coupling scheme was valid only for elements up to bromine, that is elements like which have low quantum numbers. What about the elements which have higher atomic numbers? In that case, there is another scheme which is called the JJ coupling. In this case, the individual angular momenta combine first. That means for each electron, you will first combine its orbital angular momentum with its own spin quantum number and get a small j quantum number. When we talk about a single electron, we use the small letters, the lowercase letters, and when we talk about the combined system, we use the capital letters. So we are talking about each individual electron will combine its L and S values. Once you have got all of these, then you get the total J, the capital J quantum number, again by combining all the Ji's, and this is done for 2 electrons, J1 plus J2 up to J1 minus J2, and this is the scheme which is valid for heavier elements. We will not go for this scheme because we will only take up the lighter electron atomic number atoms, and it is far easier. What I have shown here is that we combine J is equal to L plus S, and it is the vector addition looks very complicated, but it is much easier to combine the MS and ML values, and I will show an example just now. Now, what is the, first we will talk about what is the information. Why are we taking the trouble to write down the term symbols? One is of course convenience. You should not be writing down the whole electron configuration for sodium, potassium and so on. It is sufficient to know how many unpaired electrons are there in which orbital and so on. We only need to know the values of L quantum number, the S quantum number and the J quantum number, because later on we will show that spectroscopy depends only on these quantum numbers. It does not depend upon the individual electron configurations, it depends upon these quantum numbers. These term symbols provide three pieces of very vital information. One is what is the total orbital angular momentum L, what is the multiplicity of the term, the S quantum number gives us 2s plus 1, and the total angular quantum number which is J. Now, how finding the ground state term symbol is very easy because we know Hund's rules, which tells us that how we place the electrons in different orbitals if they have the same energy or they have different energies. The first cardinal rule is that the full shells and subshells do not contribute to the overall angular momentum. So we don't even worry about them. I've just told you that for carbon, for example, we will not look at 1s2, 2s2 because they are completely filled. We'll only be looking at the 2p2 electrons because these are not completely filled. For helium, we only have 1s2. So it is completely filled and it has all such systems will have only one electron configuration, and that is equal to 1s0. They are always singlets, their total orbital angular momentum sums up to 0, and the J value can only have one value, and this is equal to 1s0. So helium, any inert element where you have completely filled orbitals, even beryllium, they will have 1s0. You don't even have to worry about finding out the ground state term symbol. Now, for example, for sodium, we do not look at, we are looking at the ground state term symbol that I had just written. We disregard the filled orbitals and keep only the 3s electron. The S, obviously S becomes equal to half because you have only one electron and it has a spin quantum number of half. L is equal to 0 because we are talking about an S electron, and J is equal to L plus S can have only one value because L minus S will also have the same value. It will be minus half, but remember we are looking at the absolute value. So J is equal to half only. So we write down its state symbol as 2s half. It is a doublet because 2s plus 1 is equal to 2. We say that it is a doublet and its ground state term symbol is 2s half. Now we come to the ground state term symbols of other elements. Helium, again ground state is 1s2. We don't even worry about finding out, we know that it is completely filled, so it is 1s0. It is a singlet state, it has a total orbital angular momentum of 0, so it is an S state, and its J quantum number is equal to 0. Carbon with 1s2, 2s2, 2p, the 1s and 2s levels are completely filled, as I said, so you only worry about the 2p orbitals and we have to fill them with 2 electrons. How do we fill them up? The 2p electrons, the 1s and 2s we have disregarded. We are looking at the highest occupied level, which is the 2p level. Now here there are 3 orbitals. The L value is equal to 1, so the ML values are equal to plus 1, 0 and minus 1. Remember these values are plus L to minus L. The first orbital that I have shown on the leftmost position, we will first fill an electron there, we will put an electron with spin up there. The second electron we will not put in the same orbital because we will have to put it with spin down. This will not give you the ground state energy. Hund's rule of maximum multiplicity tells you that keep on filling up degenerate levels with electrons of the same spin until you have exhausted all of them. So the second electron goes to the second orbital which has an ML value of 0. So its total I told you that it is much easier to talk in terms of the addition of the ml and the ms values, because it is much simpler than adding up the l and s values, where you have to do vector addition of the total angular momentum. So now our ml1 value is equal to plus 1 for the first electron and plus 0 for the second electron. So the maximum value of ml turns out to be equal to 1. Now that means that the L quantum number should be equal to 1. The ml value of 1 is one of the components of the L is equal to 1 quantum number. So its L value should be equal to 1. Similarly for S, ms1 plus ms2 should be equal to half plus half, and that should also be equal to 1, because you have both electrons with alpha spin, which we arbitrarily call as ms is equal to plus half. So half and half, it gives you a 1. Now the J values which are possible are what? The L value is equal to 1, the S value is equal to 1, and we had seen that J values can start from L plus S, keep on decreasing 1 unit until you arrive at L minus S. So L plus S is equal to 2, 1 plus 1, you subtract 1, you get 1, you still do not have L minus S, which was equal to 1 minus 1, which should be equal to 0. So you subtract 1 again and you get 2, 1 and 0. Now the term symbol, so there are 3 term symbols which are possible. Our L was equal to 1, so we call it a p state. The S value was equal to 1, so the spin multiplicity was equal to 3. But we have got 3 values of the J value, that means we can write down 3p2, 3p1 and 3p0. Now how do we decide which is the ground state? Again, Hund's rule comes to our rescue. It tells us which one to assign as the ground state, because they are not degenerate. One of them will have lower energy and the rest will have higher energy. So how do we assign them? Hund's rule tells us that the lowest energy term is that which has the greatest spin multiplicity. For terms that have the same spin multiplicity, the term with the highest orbital angular momentum lies lowest in energy. Here we are talking about the ground state, so this does not apply. When spin orbit coupling takes place, which is more pronounced for the heavier nuclei, it splits the energies into different levels corresponding to the J values. The level with, if you have an unfilled subshell which is exactly or more than half full, then the one with the highest J value, it has the lower energy. And if you have an orbital which is less than half full, in that case the one which has a J value which is lower will have the lowest energy. I'll repeat this. The energies of different kinds of term symbols that you can derive from the P2 configuration, they will have different energies. Hund's rules tells us which ones have lower energy. In this case, we are looking at the ground state. So what we have arrived at is different term symbols which have the same values of S and P, but different values of J. Now when they have different values of J, how do we decide which J value has the lower energy? What we do is that we look at the orbital and see whether it is half filled or more than half filled. If it is less than half filled, then the lower J value is the ground state, and if it is more than half filled, it is the higher J value which is the ground state. Now since 2p orbital, now it is less than half full, you can have a total number of 6 electrons in a 2p orbital, and you only have 2, it is less than half filled, it only has 2 electrons when it can hold 6 electrons. In that case, we will decide that 3p0 is lower in energy as compared to 3p1 and 3p2. So the order of energies is 3p0, 3p1, 3p2. 3p0 is the lowest in energy. Again, let us look at the ground state of some other elements. Beryllium, both of them are completely, the 2s electrons completely are occupied by 2 electrons, and so it is a 1s0 state. We said when something is completely filled up, we don't worry about it. It is always a 1s0, a singlet state. When we go to boron, you have 3 electrons to be filled in 2 orbitals, because boron has an atomic number of 5. What it means is 2 electrons you put in the 1s orbital, you are left with 3 electrons. The 2s electrons are completely filled, so there is only 1 electron which we look at. This 1 electron is has an ml value of +1, always assign +1 to the first electron. Ml is equal to +1, so the total angular momentum, orbital angular momentum is equal to 1. It becomes, since ml is equal to 1, it becomes a p state because L is also equal to 1. There is one unpaired electron with an ms value of half, so S is also equal to half. 2s plus 1 is equal to 2, and since S is equal to half and L is equal to 1, you have 1 plus half, 1 plus half and 1 minus half, that means 3 by 2 and half. These are two values of the J quantum number that you can have, but since this 2p orbital is less than half full, we assign 2p half to the ground state. Coming to nitrogen, there are 3 unpaired electrons. The total value of the ml quantum number turns out to be +1 for the first electron, +0, -1, which is equal to 0. So L is also equal to 0, it becomes an S state. The number of unpaired electrons is 3, so the spin quantum, ms quantum number is equal to 3 by 2, and 2s plus 1 turns out to be 4. J value, for half filled, it doesn't matter whether you take the higher value or the lower value, it will give you the same number. So 4s 3 by 2, you get only one number because S contributes only 0, 3 by 2 is, S is equal to 3 by 2 and L is equal to 0, L plus S and L minus S have the same value 3 by 2. So we get for nitrogen the 4s32 state. For oxygen, now look, oxygen and carbon, they have a similar electron configuration in the sense that in carbon you have 2 electrons that occupy 2p orbitals, while in oxygen you have to put in 4 electrons because oxygen has a 2 higher atomic number as compared to carbon. Now you will have 2 electrons, if you look at, you will have to put in 4 electrons, you will put in the third electron in the ms is equal to -1 orbital and the fourth electron back in the ms is equal to 1 orbital with a different spin. Again you have 2 unpaired electrons, so you again get 3p2, but 3p2 becomes the lower energy level because now it is more than half full. You are putting 4 electrons in a 2p orbital and there is a possibility of putting 6 electrons there, so it is more than half full, and unlike carbon where we said that the ground state is 3p0, it is equal to 3p2. We also have the concept of holes and electrons. Here in the case of carbon you have filled in 2 electrons and there are 4 more vacancies in the 2p orbitals which normally spectroscopists call holes. There are 2 electrons and 4 holes. In the case of oxygen you have 4 electrons and 2 holes. It doesn't matter whether you have 2 electrons and 4 holes or 4 electrons and 2 holes, the term symbol will be the same. The only thing that will be different is that which is the J value that you will assign to the ground state, and in this case it is 3p2 whereas it was 3p0 for the case of carbon. Now the 2p2 configuration, we were talking only about the ground state. Ground state is relatively easy to find out, but what happens when we go to the 2p2 configuration and try to find out all the states that come from this configuration? Because this is very complicated, we'll first take up a simpler case where we talk about 2p1, 3p1 excited state of carbon. Now what happens in this case? You have n quantum number which is different for the 2 electrons, and this means that both the electrons can have alpha spin or beta spin, they can have the same spin. The total number of terms which is possible is, because the p orbital can accommodate 6 electrons, that means that the 2 electrons can be accommodated in any one of these spin orbitals, and the total number of electrons that can be accommodated, number of states that is possible, will be equal to 6 into 6, which is equal to 36. Now 36, and what are the terms which are possible? Since ml1, your L is equal to 1 for the first electron, L is also equal to 1 for the second electron. The possible values of L are equal to L1 plus L2 up to L1 minus L2, that means 2, 1 and 0. S, because both the electrons have half spin, half plus half up to half minus half. So 2 possibilities of spin are possible, 1 and 0. Both these possibilities mean that you can have terms which are 3D, 1D, it can be a singlet or a triplet D state, it can be a singlet or a triplet P state, it can be a singlet or a triplet S state. The total degeneracy of a state is given by 2s plus 1 into 2l plus 1. So a 3D state has a degeneracy of 3, the spin degeneracy. For a d orbital, the L value is equal to 2, so the degeneracy is equal to 2 into 2 plus 1, which is equal to 5. So 3 into 5, the 1d has a degeneracy of 1 spin into 5 and it becomes 5, and for 3p it is, the spin degeneracy is 3, the orbital degeneracy is equal to 3 because 2L plus 1 is equal to 3, and so on. When you add up all these degeneracies, you get 36. This is something that when you are doing a calculation, you must check, because otherwise if it does not add up to what you had predicted, you are making some mistake somewhere. So all these states are possible. What did Hund's rule tell us? That first you look at the spin. The orbitals, the terms which have the higher spin multiplicity are lower in energy, and this means that 3d or 3p or 3s, one of these will have the lower energy compared to 1d, 1p and 1s. Now, how do we decide which one of these is lower in energy? We look at Hund's second rule. It says if they have the same spin multiplicity, we will now look at the orbital multiplicity, and the one with the higher orbital multiplicity will be lower in energy. So that means 3d will be lower in energy as compared to 3p, and this will be lower in energy as compared to 3s. First we look at the spin multiplicity. Out of all the terms which have the same multiplicity, the one with the higher orbital multiplicity will be lower in energy. So out of all these states, the one with the lower orbital spin multiplicity is 3d, and so the ground state of carbon in this excited state should be equal to 3d. Now, it is not so simple for 2p2 configuration. In the case of 2p, 3p, the n quantum number for the two electrons was different. Since the n quantum number for the two orbitals was different, we were able to have both spin up and spin down configurations for both the electrons. It was possible to put both electrons with alpha spin or both electrons with beta spin, because at least one of the quantum numbers was different. Now, if it is a 2p2 configuration, both the quantum numbers are, n quantum numbers are the same. So now we have some restrictions that you cannot have all the 4 quantum numbers the same. In this case, the total number of possibilities is given by the combination. 6 is the possibility, the total number of electrons that can be filled up in a p orbital, and you are choosing any 2. So it is 6c2, which is equal to 15. So from 36, now we have gone down to 15, and we have to see that some of the terms which were possible for the 2p 3p configuration become they are not allowed for the 2p2 configuration because of restrictions of Pauli exclusion principle. Now, what are the terms? To do this, we have to explicitly write down what are the possibilities. Now, ML has 3 different possibilities. ML can have 1, 0 or minus 1 values, and for each one of them, MS can have half or minus half value. So we have made a table here where we put in ML is equal to 1, 0, minus 1, and for each one we've written half, minus half for the spin, and we put in electron. If I put one electron in an ML orbital with an alpha spin, the second electron cannot also have an alpha spin, so we put it with beta spin. It is like having 2 electrons in the ML is equal to 1 orbital, with one having alpha spin and the other having beta spin. Now, if you have want to add another electron with the same spin, you have to put it in a different ML value, and you put it in the one with ML is equal to 0. Now, both of them can have MS is equal to half. Similarly, we look at all the possibilities, taking care that we are not putting 2 electrons with the same MS value in the same orbital, and this is the 15 configurations that we get. Now, we sum up the ML values. The ML values, as we said, were equal to summation Mi. For the first configuration that we got, both the electrons were put in the ML is equal to 1 orbital. So the total ML value is equal to 1 plus 1, which is equal to 2. Since both of them had different spins, plus half and minus half, half minus half, the MS value is equal to 0. For the second one, we have put one electron in ML is equal to 1, the second one in ML is equal to 0. So the total ML value is equal to 1. The MS value is equal to 0 because one had alpha spin, the other had beta spin. The third one, is again ml is equal to 1, and the second electron has an ml is equal to 0, but in this case one has alpha spin and the other one has beta spin. In this case the ms is equal to 0, and you can just keep on adding up the ml values for the two electrons where we have put the crosses and the ms values for the two electrons where the crosses are there, and write it beneath in that column where I have written ml is equal to summation mi and ms is equal to summation ms. When you do that, you start, now how do we get the allowed term symbols? You start with the maximum ml value. The maximum ml value here was equal to 2, because see I am reading out 2 1 1 0 0 1 1 0 0 0 minus 1 minus 1 minus 1 minus 1 minus 2. The absolute magnitude of both of these was equal to, the maximum value is equal to 2, and for ms is equal to 1. I look only at the ml value, and ml is equal to 2. Look at the ms value corresponding to this. The ms value corresponding to this is equal to 0, and that means that the s value is equal to 0, and it is a d state with an s value is equal to 0. So the first state that I have obtained is a 1D state, because the s value is equal to 0, it becomes 2s plus 1 is equal to 1, and it is a D state. It has a degeneracy of 5, because the spin multiplicity is equal to 1 and the orbital multiplicity is equal to 5. So 5 states belong to this category, and which ones are these? The L values can, ml values can be 2 1 0 minus 1 minus 2. The corresponding s values can only be 0 0 0 0 0, because ms is equal to 0, s is equal to 0, it can only have one component which is equal to 0. So out of, by writing down 1D, I have removed 5 of the states that we were talking about, and then we cross off these 5 microstates and then see which ones we are left with. Again look at the maximum ml value. In this case the maximum ml value is equal to 1, but the corresponding ms value is also equal to 1. So the spin multiplicity has to be equal to s, 2s plus 1 is equal to 3, and ml is equal to 1, so it is a p state. So now we are talking about a 3p state. A 3p state has a degeneracy of 9, that means 3 is the degeneracy for the spin and 3 is the degeneracy of p. The ml values can take on values 1 0 minus 1. Similarly ms can also take on 1 0 and minus 1, that is why there are 9 states present here, and this gives us a 3p state. Once you've removed all these, you are left with only one microstate. These are called microstates, and this is 0 0, and 0 0 can only correspond to an ml value of 0 and an ms value of 0, which is equal to 1s 0. Now each term 1d 3p 1s defines a state. This has these are all microstates which have the same energy. 3p has the same energy, all the microstates, all the 9 microstates have the same energy, all the 5 microstates of 1D have the same energy, and similarly the 1s microstates have one energy. I think
time is over, so we'll continue tomorrow lectures. So well friends, as you heard today, we discussed atomic spectra, but some part of it has been left, so we'll continue with it. So I thank all of you for watching the lecture, and on behalf I thank Dr. Rita Kakkar for giving such a wonderful lecture. Thank you very much.
thank you.
Students, here are some questions related to your topic. First, 3 are multiple choice question. Question number 1, the series corresponding to minimum wavelength transition in hydrogen atom is, first option is Balmer series, second option is Lyman series, third option is Paschen series, fourth option is Brackett series. Now the next question, the ratio of minimum wavelengths of Lyman and Balmer series will be, first option 1.25, second 0.25, third 5, fourth 10. Now the next question, the maximum wavelength of Lyman series is, first option 4 by 3R, next 1 by R, third C by R, next 1 by RC. Now the next question, write the Rydberg formula for the spectrum of the hydrogen atom. Now the last question, Calculate the shortest wavelength in the Balmer series of hydrogen atom in which region, whether infrared, visible, ultraviolet of hydrogen spectrum does this wavelength lie? Thank you.